-1 meters. Okay, you are supposed to calculate electrostatic field at this very point. Okay, I'm sure you will be able to do this example. Okay, so this example will stay as a home assignment for you. Okay, so try this out. Later on we will be repeating these examples. Okay, now let's switch to another point, and that is electrostatic potential due to a point charge. Again, we do not to we do not derive it out. Okay, or rather we can derive it out. Okay, so simply electrostatic potential, electric potential due to a point charge is equal to this. At any point we can define it like this: V at R is simply, the simplest definition is this, minus times integration of E dot dr, E dot dr. Okay, and then this E is the electrostatic field due to a point charge. And what is the electrostatic field due to a point charge? That's equal to K multiplied by Q divided by radial distance square, so R square multiplied by R cap, where R cap is a unit vector that is directed radially outwards. Okay, then this dr can be written like this as well. We can write down this dr like this, something like this, dr multiplied by R cap, isn't it? Okay, so it is equal to dr multiplied by R cap. Then from there we can calculate the electrostatic potential like this. अच्छी तरह से यहाँ ध्यान रखना बेटा. Okay, then here we can calculate the potential at which is R. So V at R will be equal to what? That will be equal to minus times integration of, now electrostatic field can be replaced by this KQ divided by R square multiplied by R cap, then dot product with what? Dot product with the dr multiplied by R cap. Okay, then R cap dot R cap is obviously equal to 1, so this will be entered equal to minus KQ integration of R is to the power minus 2 with respect to R, and the limits of integration from infinity to point R. Fine. Okay, then what I can write is this, then finally the situation will be equal to KQ divided by R. Okay, you can do it yourself, like R is power minus 2, its integration is R is power minus 1 divided by minus 1, negative sign will be absorbed, then it's 1 divided by R, final limit, this will be here, then upper limit minus lower limit, so lower limit will simply vanish because 1 by infinity is 0, so it will be 1 by R. So finally the potential at any point R due to a point charge is simply equal to KQ by R, or we can also write it like this, it is equal to 1 by 4 pi epsilon naught divided by Q divided by R. And this also implies an important point here, that this potential due to the point charge is proportional to 1 divided by R, something like this. Okay, so this is the electrostatic potential due to a point charge. Fine. Okay, let me plot a graph here as well for this, for the electrostatic potential with V versus R. Okay, so here I will write down plot V as a function of R versus R graph. Okay, so easily we can plot the graph. We can plot it like this. So here we have, along the horizontal direction, along the horizontal axis I will take R, along the vertical I will take V as a function of R. Now obviously it's proportional 1 divided by R, that means it will be a rectangular hyperbola like this. Okay, but there will be slight difference between the field graph and the potential graph. So if this is a potential graph, the field graph will be something like this because it is 4. Okay, so this here what? This here potential proportional to 1 divided by R, and this here field proportional to 1 divided by R square. This one represents field proportional to 1 divided by R square. The reason is that electrostatic potential due to a point charge is equal to KQ divided by small r, and field due to a point charge is equal to what? Field due to a point charge is equal to K multiplied by Q divided by R square. So that means both V is proportional 1 divided by R and E is also proportional 1 divided by R square. But the difference being that this field 1 divided by R square, so the difference in the graph will be that the steepness of the graph will be more compared to the potential. Okay, so this will be here field versus R graph, and this will be our potential versus R graph. Okay, so I think it's clear to you and it's elementary. ठीक है ना बेटा? Okay, तो इस पर उतनी ज़्यादा हम मतलब discussion नहीं करने जा रहे हैं. Okay, why I am teaching this to you? Because we have to go switch the superposition principle, and the safely questions have been asked in on superposition principle in competitive exams. Okay, that's why. ठीक है ना बेटा? Then elementary questions are also asked in the competitive exams. Okay, like this it is. Now superposition principle for electrostatic potential in one line I can simply write it like this: that the potential at any point R, because of the n point charges, will be simply equal to summation of Vi, where I runs from 1 to n. Fine. Or I can write it like this as well. It is simply equal to summation of I runs from 1 to n, and then here I can write down KQ divided by Ri, something like this. Okay, so this is the potential at any point R. If we assume that the point charge is like, if we assume that this suppose and this at any point R, so we want to calculate potential at any point R. Rather, this R is the position vector of the origin. If it is origin, then we can calculate like this. If it's not origin, still we can calculate. Okay, still we'll do example for this. Okay, so we are done with what? Number one, electrostatic potential is the point charge, and what's that? That's for KQ by R, or 1 by 4 pi epsilon naught Q divided by R. and this will be the graph V versus R graph, and this will be the field versus R graph as well. Okay, then here the superposition principle is simply like this. Okay, so suppose that you want to calculate electrostatic potential due to n point charges. Fine, what you do is this: step number first is that identify first of all how many charge particles are there, then calculate the electrostatic potential because of 1 point charge, assuming that another charge, the rest of the charges are not there or not, they are absent. Then calculate the electrostatic potential because of the another point charge. Then calculate the electrostatic potential because of another point charge, and then take the simply scalar sum. The reason is that electrostatic potential, it's not a vector quantity, it's a scalar, and remember that it is always easy to deal with the scalars compared to vectors. Okay, always easy to deal with the scalars compared to vectors. Okay. So now we are done with the superposition principle. Okay, let's do some examples on the superposition principle. Concentrate here. Okay, let's do some examples of superposition principle. Like this is example number 1. Example number 1 is like this. For example, here we have 2 point charges. Simplest example. These are 2 point charges. Here we have 1 point charge. Here we have another point charge. This is Q. This is Q. Fine. And you are supposed to calculate electrostatic potential at point P. Electrostatic potential at point P. This distance given to you, that's called A and A. Yeah. Okay. Can we calculate electrostatic field at the point P? What will be the electrostatic field at point P? Electrostatic field at point P will be obviously equal to 0, isn't it? Because electrostatic field because of this Q will be equal to KQ by R square, A square rather, towards right, and the electrostatic field because of this point charge will be equal to KQ by A square towards left, and the two fields are equal in magnitude, opposite direction. They are going to cancel, hence the net potential field at the point P will be obviously equal to 0. But if we calculate potential at point P, calculate first of all potential because of 1 point charge, that will be equal to KQ by A. Calculate potential because of another charge, that will be also equal to KQ by A. So they will add like scalars. They simply behave like scalars. Fine. Now this is simply twice KQ by A. That's it. Twice KQ by A. So this is the potential at point P. Okay, done. Example number 2. Example number 2 is like this. Suppose that here we have 2 point charges like this. Here we have 2 point charges. Like for example, this here minus Q and this one is plus Q, and this here point P. This simply what this is. This is just the warm up of the electrostatic potential problems. And this here point P. You cannot expect such a question to be asked in the competitive exam. Okay, but I want to teach you an important point here. That's why I'm showing these 2 examples. So here we have this is A and this is A. Now the question is like this: calculate the electrostatic field at point P and calculate the electrostatic potential at point P. Fine. So electrostatic field at point P will be obviously equal to what? Because of this plus Q, it will be towards left, and because of this minus Q, it will be also towards left, attractive field. So electrostatic field at point P will be equal to twice KQ by A square, where KQ by A square is the field because of this charge, and KQ by A square is the field because of this charge, and that in the same direction, so they are going to add. So the field at the point P will be equal to twice KQ by A square. Now the potential at point P, because of this minus Q, will be equal to minus KQ by A. Simply electrostatic potential because of negative charge is negative, and electrostatic potential because of positive charge is positive, and because of plus Q, it will be obviously plus KQ by A, and that's simply equal to 0. So from example number 1 and 2, this is an important point which follows. And that's like this. If for example, suppose that I will say like this: if electrostatic field, if electric field at any point is equal to 0, does it imply that the potential is also equal to 0? Does it imply? No, it's not necessary. If the electrostatic field at any point is equal to 0, it's not necessary that the potential will be equal to 0. Potential may or may not be equal to 0. Like this it is. Here we have the electrostatic field at the point P is equal to 0, but the potential is not equal to 0. In the same way, suppose that we have a hollow sphere, uniformly charged hollow sphere. Electrostatic field inside will be equal to 0, but the potential inside is not equal to 0. That's rather constant. Okay, so if electric field at any point is equal to 0, it does not imply that the potential is equal to 0. Potential may or may not be 0. In the same way, if the question is like this now, if the potential at any point is equal to 0, does it mean that the field is equal to 0? No, it does not necessarily mean the electrostatic field will be equal to 0. It does not necessarily mean that the field will be equal to 0. The example second is the evidence. Okay, so at this point, the electrostatic field potential at the point P will be equal to 0, but the field at the point P is not equal to 0. Okay, so these are 2 important points. Point number 1 is this, and point number 2 is this: if electrostatic field at any point is 0, it does not necessarily mean the potential will be equal to 0, because the reason is that differentiation of a constant can even be 0. So if electrostatic field in any region is equal to 0, it does not necessarily mean the potential will be equal to 0. Potential in that region can be 0, but it can be constant even. Okay, so that if you calculate the differentiation of that potential, that will be equal to 0. Okay, so that the field is equal to 0 in the same point number second. Fine. Okay, now I think example number point number first and in year 2017, and that to hide this example. Okay, easiest of the lot. Okay, now up the bit. Okay, so let's do this example. Dipole nahi padha hai. Okay, the reason is that we'll be studying that in the multiple expansion. We'll be first of all calculating the electrostatic field and electrostatic potential due to dipole, then due to quadrupole, and then due to octopole, and then we'll be having some important results there because continuously questions are asked on that. Okay, in all the competitive exams. Okay, then I'll show jugaad technique how to do those examples in the competitive exams. Like this, okay, here we have this a question that's asked in year 2017. What is the question is like this: Latin charges are placed at 5 vertices of an hexagon. So there's a hexagon, obviously the 6 corners, but the 6 charge particles are not there. There are 5 charge particles which are placed at the 5 corners of the hexagon. The magnitude of electric field and electric potential at the center of hexagon is. You are supposed to calculate what is the electrostatic field, magnitude of electrostatic field, and magnitude of electrostatic potential at the center of hexagon. Let's first of all make a diagram here. Okay, so that it will be clear to you. Okay, so that it will be clear to you. Like this, it is. For example, here we have this regular hexagon. This regular hexagon whose side is given to it's equal to A. And moreover in the hexagon, for example, this hexagon, its side is A. आपको याद क्या रखना है बेटा? So this is a point. For example, this is the center point, which is point P. Okay, center point or point O, 117. This distance also equal to A. Okay, the distance of the corner from center point in case of hexagon, that's also equal to A. So that means this distance A. Now it is given to you that there are 5 charge particles. So 1 here, 2, 3, 4, and 5. So there are 5 charge particles at the 5 corners of the hexagon. Right? The 6th corner is empty. Now you are supposed to calculate what electrostatic field at the point O and electrostatic potential at the point O. If you are interested in calculating electrostatic potential, that's not a big deal. Easily you can calculate electrostatic potential at point O. That will be simply equal to what? What is the electrostatic potential because of this charge? That's obviously equal to KQ divided by A, isn't it? So simply multiply by 6. It will be simply 6 KQ by A. Why? Because there are 5 KQ by A. I'm sorry, because there are how many point charge? There are 5 point charge. Obviously, it will be equal to 5 times KQ by A, and all those charge particles have same magnitude, and all those charge particles equidistant from the center. So this is also at a distance of A. This is also at a distance of A. This is at a distance of A. This at a distance. So that's why 5 times KQ by A. Or we can write it like this as well. Potential at the center point at point O will be how much? It will be also, we can write like this: 5 times Q divided by 4 pi epsilon naught multiplied by A. So this is the potential at the point O. And then you want to calculate what electrostatic field. Safely we can calculate the electrostatic field, but using a jugaad. So for example, here we have the 6th corner. At the 6th corner, what is the charge here? That's equal to 0. But this 0 charge can be replaced like this. Can I write it like this? It is equal to Q minus Q. Can I write like this? Because Q minus Q is obviously equal to 0. Now the electrostatic field at the point O, because of these 6 charge particles, 1, 2, 3, 4, 5, and the 6th charge particle is obviously equal to 0 by symmetry. So we are left with now this system reduced to this. This system is equivalent to this. So here we have point O, and then here at the 6th corner there's only 1 charge particle, which is minus Q. Now there will be electrostatic field at point O whose magnitude will be equal to how much? Whose magnitude at the point O will be equal to simply KQ by A square. That's it. KQ by A square. And this electrostatic field will be directed towards the empty corner. So it will be directed in this direction. Direct towards empty corner. The reason is that electrostatic field due to the negatively charged particle is attractive in nature. So this is the electrostatic field vector. It is direct towards minus Q, or it is direct towards empty corner. So that's equal to this, or we can write it like this as well. It's equal to 1 by 4 pi epsilon naught multiplied by Q divided by A square. So that's it. We are done with this. So we have calculated both the electrostatic field as well as electrostatic potential. Electrostatic potential simply is there are how many charge particles? 5 charge particles. So because of 1, it will be equal to KQ by A. It simply behaves like a scalar. So all the 5 will add. So it will become 5 times KQ by A. Then if you are interested in calculating field is a vector quantity. So accordingly, we will have to play with it. So this is an empty corner. At the empty corner, the charge is equal to 0. So this means it can be written like this: Q minus Q. Now the electrostatic field at point O, because of these 6 charge particles, except this minus Q, is equal to 0. Okay. Then we are left with only 1 minus Q. So the system is equivalent to this. This here minus Q electrostatic field will be obviously equal to KQ by A square. Hence we are done with this problem as well. Fine. Okay. You can do a number of examples on the continuous system. Few examples for you as home assignment. I'm sure you must be able to do those examples. Okay, so I'll keep those examples as home assignment for you. I'll not be showing those examples. Okay, they are just childish. So another example can be like this as well. Suppose that here we have this corner, this square here, and there are for this charge particle q minus q, and here it is supposed to, and you are supposed to calculate electrostatic potential at point P. You are supposed to calculate simply potential at point P is equal to what, and the side of the square that is given to you is equal to A. But safely you can calculate. It's not that big. Okay, then let's do one more example like this. Suppose that here we have this an equilateral triangle particle something like this 3q, here it is charged 2q, here it is charged minus q, and side is A, and you are supposed to calculate potential at point B. Safely you can do this as well. Okay, orally you can do it rather. Okay, then there is then here let me give an example. Here there's a dipole, electric dipole. So you yourself calculate the electrostatic potential at two different points like this. It is this here minus q charge and this here plus q charge. So this is a dipole, and this distance given this A, this is the center of the dipole. Calculate the potential at the 2 points. One is at this period point. Suppose this point is point A, and this another point here. This is point B, and this here distance R, and this distance also given to you, that's equal to R. So you are supposed to calculate what is the electrostatic potential at the point A, and what's the electrostatic potential at the point B. Okay, so try this yourself. This is a home assignment for you. Okay, so we are running out of time. We are less than 1 minute, and then tomorrow's topic will be electrostatic potential due to continuous system. Okay, then at the end we'll be doing some examples which have been asked in the competitive examples like this one. This has been asked in the IC. Okay, in 2008. Then this one, this is David Griffith problem. Okay, so you take care of yourselves. So tomorrow the topic will be electrostatic potential due to continuous system.